Good afternoon, everybody. It gives me great pleasure to introduce this afternoon a seminar being given by Professor J Queisser from the Max Planck Institute in Stuttgart, where Hans is the emeritus professor and still director of the centre. Hans was born in Berlin in 1939 and studied in physics in Berlin as well, studying in physics, before he took up positions both in Kansas and then in Göttingen, where he did his PhD in 1958. He then joined the Shockley Transistor Corporation, where in 1961 he did the work on detailed balance work and published that work that we are all very familiar with, on the detailed balance work.
Actually earlier, but it was rejected at first, I'll tell you that.
Right.
Yes.
We'll hear more about that next Monday, I think.
Next Monday, yes.
Okay. And then in 1963 he joined Bell Labs, before being given a professorship in Frankfurt. And then becoming one of the founding directors, of the Max Planck Institute for Solid State Physics in Stuttgart, where he's still the emeritus professor at this day. And so I'd like to introduce J Queisser, who will give us a talk on hot carousels. Thank you very much.
To be here is an honor, because we know that you people here are doing the very best work on solar cells. First, second, third generation. I wish you much luck with the later generation. We all look at you. And we had some interaction, although the distance between Stuttgart in southwestern Germany and Sydney here is quite long. Some of my people went here. If anybody remembers Ralph Bergman, he was here and he's now a professor at a German university. And Andrew Blakers, on the other hand, came to join my group when we did some work on solar cells in Stuttgart. So, multiple carrier generation in solar cells. I want to give you a little bit of an input of some work that we did some time ago, and that is still interesting, especially for you experts here. Now, let's see. The solar cell is actually a pretty dumb device. If you look at it from the standpoint of silicon microelectronics, which was also my field. I grew up with Shockley in the old apricot barn in Mountain View, California, which is now the cradle of Silicon Valley. At that time, we would not have believed that silicon could be used to such an extent, to such wonderful performance. Now, a solar cell has just one p-n junction, harmless. It is a two-terminal device, which has definitive disadvantages in microelectronics. It is not exactly a high-speed device, as for example, a modern microprocessor has. There's a rather low frequency of operation, namely 0. It's a DC device. So from the standpoint of, say, an Intel person. Many of my good friends are at Intel in Santa Clara, California. And look and see, a solar cell. However, solar cell is a wonderful device, on the other hand, because it can convert, you know this of course, but I have to stress it again, because it can convert solar radiation directly, without noise, without waste, directly into electrical energy. And that, of course, is your effort here, which everybody admires. And again, I wish you luck. And I want to talk a little bit about the better utilization of solar spectra. When you do a simple theory of a solar cell, you have to somehow match it to the sun. And that's what we did in 1960, 1959 even. I started when I joined Shockley, and I'll tell you later in next week a little bit about anecdotal evidence and other things. Shockley said, here, I want to do solar cell work. Most of the money of our government contract is spent, but we have no results yet, so go to work, which I did. So if you do a simple theory to match the semiconductor material to the sun's spectrum, you have a one-parameter theory, namely just the energy gap, which is the quantity of importance for a semiconductor material. You have to find out what is the optimal energy gap that is useful for catching and utilizing solar radiation. if you choose this energy gap too low, you get hardly any voltage out, as you very well know. If you choose it too high, you lose much of your photon input because it cannot be absorbed. So you have to do some calculations, and that's what we did, that other people did in the late 50s, early 60s. There's a broad maximum in which silicon is a part of, but also other materials. And at that time, when I started working on it, there was still quite a bit of controversy. What would be the best material? So I did not work from the very beginning on solar cells. The first solar cells were made at Bell Laboratories in 1954 by my good friends Calvin Fuller, George Pearson, and others. And it was not really of any interest at that time. I'll tell you a little bit about that later. But one thing became quite clear when we started working, that you use only a small portion of the energy input from the sun, as you know very well. The blue part of the spectrum is used, but inefficiently, because only one pair per photon is assumed. That's what we did in our theory, just one pair. The rest of the energy that comes in is lost, and it's lost to heat. It increases entropy. And what our noble task as engineers and scientists is to reduce entropy wherever we can. It's a tough job, it takes energy, but that's what we have to do. And we'll see how one can try to do that. The red part of the photon spectrum of the sun is inefficient because it cannot be absorbed. Some people say, yes, you put some deep centers in the middle of the gap, but I don't like that, as you may know. I think that recombination is enhanced more than you can get. So what do you do in order to better utilize the solar spectrum, which, by the way, we already mentioned in our 1960 paper, which was after rejection eventually published in 61. So one thing is to use multi-junction cells. Again, a topic well known to you. You put several junctions, stack them up on top. Beautiful work is being done here, but also in Japan by Yamaguchi and his people. Very nice work, I must say. I like this work. Small laboratory, but he did very good work. And recently, something like 41% efficiency has also been achieved in Golden, Colorado, your American competitors, and at Freiburg in southwestern Germany with the Fraunhofer Society. That's the society that does applied science work, whereas the Max Planck Society has the duty of doing basic research, but we closely work together. So in Freiburg, near the Swiss border, it's the most sunlit town that we have in Germany. So they have also done some rather nice multiple junction work. And what is the idea? You first start, when the sunlight comes in, you first absorb the high energy part, find some nice tunneling contacts. You know how difficult this is. You're working on this very nicely. And then the rest of the light goes in, and at the bottom you have a PN junction that can catch the lowest energy of the incoming solar light. So these are multi-junction cells. Beautiful work, nice physics, interesting problems, but expensive. And that, of course, again, as you all know, is the big problem in solar cells. They have to be cheap, almost as cheap as plywood in order to compete with the fossil fuels. Now, carrying coal to Newcastle is not the appropriate way to say, but carrying solar cells to Kensington, that's a better way, but I'll do that. Okay, so multi-junction cells, very nice, beautiful things. Maybe one can do something with various forms of silicon like you are doing. This seems interesting, so we have to reduce the cost of these things. But multi-carrier generation is an alternative which we had looked at some years ago and which I think you people are also doing a little bit of research on. So, Sabine Kolodinsky was a PhD student. She then went to Siemens. Jürgen Werner you may know he is one of my students, working closely also together with Andrew Blakers. He is now a professor at the University of Stuttgart, and his field is also solar cells, much smaller activity than what you have here. And he likes to look at thin film silicon solar cells. Previously in his laboratory, there was some very nice engineering effort going on for CIS, copper indium diselenide, to get some engineering approach and make a very convenient and not so expensive technology. So this man has then, the collaborator of this man has then worked up in Berlin. Wittchen was at Freiburg. He did the measurements and really look at the quantum efficiency. So here you have the first plot, figure 1. We plot the quantum efficiency 0, 1 is here, quantum efficiency 1 of making a carrier pair going up to 1.6 as a function of wavelength, or if you rather want that, as a function of energy. And you see already that here we are going into the blue and near ultraviolet regime of high photon energies. So what we did was to get the best silicon we could find. We have a neighboring institution that does silicon microelectronics, and they can very nicely prepare for MOS and other things, the surfaces. So we tried to perfect a silicon solar cell by having a very well understood and very clean surface. And then we looked at it, Sabine did that, as a function of wavelength, going from long wavelength here to very short wavelength. And these are the raw data. That doesn't concern us, but you can look at it in this publication. And this is the essential part now, that curve which we demonstrate by the letter gamma. And here you see is the 1. And there are definitive parts of quantum efficiency of getting more than just 1 electron hole pair, especially here in this regime called C and D, and also a little bit at B, tiny little, but also a definite increase in the efficiency. A, B, C, D are spots or are characteristic energies and wavelength where you get more than 1 carrier pair per photon. And that's what we were looking for. We already mentioned that in our 1960 paper and said that some Russians had made suggestions but could not do experimental work, and it would be very nice if one could do that. Now, how did we interpret these figures and these? Here we have the dispersion relation, the energy in electron volts plotted versus wave vector k. This is the band structure of silicon. Arrows indicate those transitions A to D, which we have found. Let's just briefly remember what silicon is. At gamma, it has a maximum of its valence band. That's the minimum for the holes, minimum potential energy for the holes. And as you very well remember, the maybe somewhat unfortunate situation that silicon is not a semiconductor with direct optical transitions, because the electron minima are somewhere here near the X point. So electrons are housed here, nested here, holes are nested here. And recombination, very important, recombination of electrons and holes will always be accompanied by some phonon interaction. It is not a direct semiconductor. Gallium arsenide is a direct semiconductor. And just to let you know an anecdote, when we had our first discussions of the detailed balance limit, I was giving a talk at the American Physical Society in Cleveland, Ohio. It was cold there, and I was standing there, kid, youngster, and somebody got up. It was Paul Rappaport. Many people of you may know him, of the very famous and very active and very good group of RCA laboratories in Princeton. So he knew what was going on, and he said, well, Hans, what do you say? Do you think that gallium arsenide should be a good solar cell material? Because we have just shown, and they did at this particular conference of the American Physical Society, we have just shown that gallium arsenide has direct transitions. And of course, the band structure was at that time also just calculated. So maximum of electron concentration and or maximum of hole concentration and minimum for the electron concentration at the same point in K-space at gamma. So what you do? I stood there and said, believing in my own results, you said yes. Haha, he said, no, not at all true. We just did some gallium arsenide solar cells and they are terrible. We like the 2 6s. Well, what could I do? Standing there in front of all these people, just shrug my shoulders and say nothing. Now, of course, I know what I should have said, but it was premature. I would have said, dear Paul, all you have to fight is surface recombination, non-radiative surface recombination at the surface of the gallium arsenide. That is terrible. You have to overcome it, for example, by putting an aluminum gallium arsenide layer on top by epitaxy. Like later people at IBM, my good friends there, they did it and a wonderful solar cell comes about. So a direct gap with direct optical transition, semiconductor is really very nice, but silicon, let's face it, if we do it right, is also very good, although it is an indirect material. Okay, so now let's look at some of these points A, B, C, and D. For example, D was a very, very efficient multi-carrier generator. Here we see that those two lines, this conduction band part and this valence band part near the point capital sigma in the energy diagram, they are parallel. So the so-called joint density of states, joint meaning joining conduction and valence band, joint density states is very high, and therefore this is a good point to create lots of excess carriers. B and C are similar, or A, here you see close to the gamma point, also very closely parallel things. So A, B, C, and D, we could understand from the optical properties and the band structure of silicon why Sabine had measured these points as particularly useful for multiple pair generation. Okay, so it's always good to go to the basics, but how does it happen? How does it work? Again, here we plot the energy as a function of wave vector, going back really to the basics, to a band structure of silicon. And we give you the schematic of the Auger generation for second carrier pairs. You know what Auger recombination is. Auger recombination takes place whenever you have high densities of carriers. For example, you have many electrons in your device, wherever it may be, and then you look at what happens to an electron-hole pair. It must not necessarily radiatively recombine by causing a photon to go out of the crystal. No, it can transfer energy and momentum, quasi-momentum, K vector, to another electron or hole. So high density portions of any also solar cell material are dangerous because there is an additional non-radiative recombination mechanism. And again, I want to say, we want to fight non-radiative transitions, right? That's our noble idea. So Auger recombination makes a high energy electron that goes up way in the band and then comes down, tumbling down, creating again phonons. We have to avoid this recombination, which we, by the way, also mentioned in our first paper. The expert on Auger recombination resides in Southampton. Of course, you know Peter Landsberg. Of course. Yeah. Very nice gentleman, very clever, but at that time, the postal connection between Southampton and Palo Alto or Mountain View was rather slow. So, well, and he took his time, of course he had to lecture, and we wanted to wait because we thought that including this with a proper reference in our final report for the government contract was important. So I arrived at my Air Force, United States Air Force sponsor late. People didn't like that, and it says, oh, nonsense what these guys Shockley and Queisser did, so you were late, this is terrible. Okay, so Auger recombination. Now we do the inverted part the inverse Auger recombination. We call it Auger generation. Let's assume you have one high energy photon which creates an electron hole pair, electron hole, which lifts an electron out from here, from the maximum, leaves back a hole number 1, and it generates an electron which we call E1, electron 1. We have generated an electron hole pair, and in a nice way. Why? In a nice way, again, fighting entropy wherever possible, we concentrate all the energy to make this electron hot while keeping this hole cold. What does it mean, hole cold? The hole is already at its minimum energy, whereas all the energy transfer from the photon h nu goes into the hot electron E1. Now we want this electron E1 to properly and efficiently utilize its energy and momentum k to create a second electron. So energy and momentum, by this transition, losing an amount of energy and changing the wave vector by a certain specified compound, should be exactly equal and negative to create another electron going up this way and that way. So an electron is taken from here to absorb the excess energy and the excess momentum and goes up here. So this was our interpretation, and I think I'm reasonably sure that this is what happens. So we can use an Auger generation of a second carrier pair, which we call E2H2, by one hot photoexcited electron, as described in the band structure. So this can then be understood for Sabine Koller-Gdyński's data, and we published it here, so if you want to look a little bit more in detail, we think this is the appropriate condition. So we can achieve, with good surfaces on silicon and clean silicon, any possibility of non-radiative recombination must be avoided, then we can achieve a certain degree of using the excess energy of blue generated electrons for making a better solar cell. So we worked a little bit more on this and thought, well, what would be the good material to utilize to really bring out this effect very strongly? Here again, you have a recent publication, not so recent, 1994, hypothetical energy band structure of some as yet undefined semiconducting material that should approximately look like that. It should have indirect gaps, direct gaps, parallel ways of generating carriers. 2 EG, 3.5 EG should be a direct transition, and so on. The details are a little bit complicated, but that was what we said might be the optimal material to really have lots of multiple pairs. And it should have, that's very important, a lower energy, e.g., as does silicon. Why that? Would be very nice to shift our solar cell energy gap to the red. Because one, you get more of the red photons that are being absorbed because the energy gap is smaller. They contribute to the output. And B, since we have moved everything to the lower energies, lots of the green now and blue and ultraviolet photons from the sun can be utilized as multiple pair absorption processes. That's the idea. So lower energy gap to catch more red, and at the same time we try to use the blue and green for multiple pair generation. So this was very hypothetical. We looked at that and said, what could be done here? And then we thought, well, what could we do? Use another semiconductor which is readily available and has high quality. And that was an alloy of germanium and silicon. It definitely has a lower band gap. And we did some work on it, lots of work actually, quite a bit. with people like Ralf Brendel, who is now the director of another solar cell institution south of Hanover, in Hamelin. You know the Pied Piper, you have heard Grimm's fairy tales. That's where he has a new, rather nicely, and he's a clever guy, very friendly guy, so maybe he has been here, you have some contact with Brendel. And we thought, okay, let's try the silicon germanium thing. It worked, but even with great care, the enhancement of the solar cell efficiency was just maybe 1.5%. So it's not so great. And this is the trouble, of course. You all know this. If you have some activity that is complicated, you really must make a major increase in efficiency to cover the cost. We have to work with two things. We have to make highly efficient solar cells, but they have to be extremely cost conscious. They have to be cheap, in other words. And this, of course, is your essential way of working, and that's what you did. So then a new physics problem came up, which enticed me very much. I like to do that, although it's a difficult one. Question is, here we have a hypothetical band structure which looks good for multiple pair generation. Question is, can a material be found and defined which has something like this band structure? So this is a new problem of physics. It's the so-called inverse problem, which is known in mathematical physics, goes back to Mr. Helmholtz. There's a book on the inverse problem, a symposium ad memoriam Hermann von Helmholtz, very clever guy in Berlin, started many activities in Imperial Germany in physics and technology. What is an inverse problem? Well, first let's take the direct problem. You have, say, an assembly of scatterers, like a single crystal, and you shoot X-rays at it. Beautiful, everybody knows it. My boss, Max von Laue, was the first one to see it, so I'm a great fan of Max von Laue diagrams. And the direct problem is then to take the spatial configuration of your scatterers and the scattering per unit, and then calculate from it the diffraction pattern. That's the so-called direct problem. It's relatively simple. Lots of work has been done in semiconductor theory to calculate the direct problem. But the indirect problem is much, much tougher. It's the inverted thing. You're given the result of the scattering, and you have to reverse, you have to calculate what might have been the spatial arrangement of your scatterers. Very difficult, and in many cases, interesting parts of physics, for example, physiology, color vision, or now in medical physics, the signal of a nuclear magnetic resonance when you are in the tube and you get something out is also an indirect problem, but we have some idea what it might mean. But many of these problems in inverse physics are so-called ill-posed, and you can already imagine by the name ill-posed that looks kind of difficult to resolve. I don't know, and I looked a little bit into this, if our problem is really ill-posed. It may be. So you have to go in there with a preconceived idea what your semiconductor might be and how to solve this problem. At the present time, we've actually stopped working at it because I got retired. They kicked me out there, but I still have a little office there in Stuttgart. But the others took over. My young people went to Jülich, to Hamelin, to Stuttgart to do some more work, but the inverse problem was a little bit too difficult. Although Uwe Rau, who went to Jülich, is a very, very good mathematician, and I think one of you people, who is it from Jülich here, you know that Uwe Rau is a very clever guy, so I congratulate our opponents at Jülich to have captured him, but it is very difficult. So it's not resolved yet. There might be something possibly choosing a better material that really gets a much better efficiency increase than this. And it might be necessary, but I'm not sure, to use the inverse problem and its solution. So the conclusions of this small talk here. Multiple carrier generation is possible. That's very important. We could show with clean, well-prepared, nicely surfaced silicon that multi-carrier generation is possible. We've seen it. We've shown the proof. And we have understood what the basic mechanism is. It is an Auger generation problem. Yes, that's also very well known to you people here in Sydney. You need a careful technology. If you want to improve solar cell efficiencies, no matter what you do, you have to be very careful in your technology, and that tends to be costly. So the fight is to find something which is cheap and has high efficiency. Mother Nature has given us a big problem here. Lower bandgap materials are desirable. I would even say lower bandgap materials are necessary in order to catch more of the red and extend the range into the green area of the solar spectrum to make more than one electron-hole pair. What we have to fight is the electron-phonon interaction. A hot electron looks around, it is in the lattice and says, aha, there's some optical phonons, and I give my energy to them. Very well known to you. So phonon band gaps and so on, we have to really look at the details here, also of phonon physics in the coupling of electrons and holes to the phonons. So lower band gap materials are necessary, and hopefully we can somehow limit and curtail the electron-phonon interaction. But that's going to be difficult, but I think you people have some ideas on that, just as some people in Singapore do. And this is, on the other hand, a very disillusioning thing, only maybe 2% efficiency for all that careful technology. So the effect is still too small, but that's not the very end of it. So if you have some time, some activity, and of course your expertise here might help us to look at this again and make the effect a little bit higher without using too much cost. Okay, so that I think is the conclusion. Thank you very much for having listened to me. And if you ever tackle this problem, I wish you lots of success.